Hi, good morning, everyone. Thank y'all for joining me for the Ammonia Synthesis webinar today. My name is Samantha Moore. I am a consulting engineer here at Bryan Research and Engineering with a focus in the petrochemical industry. And today we'll be talking about the ammonia production process, specifically the ammonia reactors, and how to model them using a kinetic-based equations. So the ammonia production process has a couple of steps before the actual ammonia reactors. The first step would be the steam reforming process. Now, we're not going to discuss the details of this, just a quick overview. The steam reforming process will take methane and create hydrogen and carbon monoxide. The hydrogen is what's going to be used in the ammonia reactor. After we've created the amount of hydrogen that we want, we will move on to the water gas shift reaction. And what this does is it's going to convert the carbon monoxide created in the methane reactor and convert that to carbon dioxide. Once we've converted most of the carbon monoxide to carbon dioxide, we will move on to the CO2 removal step. This is where we will remove all of the CO2 or most of the CO2 in the process stream. The reason for this is because oxygen-containing species are poison to the ammonia catalyst. So as you can see, each one of these steps really has a very specific reason for its placement for the downstream ammonia reactor. So again, we're removing the CO2 because oxygen-containing species are poison to the catalyst. We will then move on to the methanation and compression step. What this does is it's going to take any leftover carbon dioxide and carbon monoxide, convert that back to methane. So we'll get the methane that's converted from those two products, compress it to the high pressure that we'll need for the ammonia reactor. And then the final step is creating that ammonia. Today we'll be talking about this ammonia reaction process and then look at a little bit more detail the kinetics behind these reactions. So the overall reaction is going to be hydrogen and nitrogen will create ammonia, specifically 3 moles of hydrogen and 1 mole of nitrogen will give us 2 moles of ammonia. This reaction will occur over an iron catalyst, and this is a very exothermic reaction. The exothermic reaction part of this is why you will see that we have interstage cooling. The cooling is very important to this process as we want to make sure that we remove as much heat as possible to increase the production of ammonia. The general operating parameters, the temperature range is going to be between 750 to 930 degrees Fahrenheit. For this particular process, we're going to be targeting an outlet temperature of 910, and we'll look at that in a little bit more detail. So we're going to have this ammonia nitrogen stream coming in to bed 1. We'll then create some ammonia, get sent to a cooler. The cooler will then cool that feed, send it to bed 2, create a little bit more ammonia, and we'll repeat that process. There are multiple different configurations for this step. The one that we see here is the most general form. Generally, we'll see about 1 to 4 beds. So as you can see here, we have 3 reactor beds, which is the average, but again, you can have a range between 1 to 4. This will vary on just based on the licensor, whoever designed the process. If you do have 1 bed, instead of the interstage cooling, because it's just 1 bed, we'll have a single stage and then a tube cooled design to provide that necessary cooling for that single bed. Another configuration setup that we can talk about, aside from the number of beds, is the recycle. So as you can see now, we have our inlet stream passing through these three beds, coming out to stream 10, cooling and getting sent to a condenser. This is where there could be some slight variation. There can be one of two options. We can either send the recycle to a separator first, as we have here, or we can send the recycle back to the inlet and then send it to the condenser in the cooler. So what this condenser is doing is it's cooling the stream and dropping out any produced ammonia before recompression and being recycled. This is the most energy efficient configuration. If we introduce the recycle before sending it to a separator, that process is used when we have excess CO2 and water that need to be dropped out. When you introduce before the separator, what happens is you're going to need more compression because you will now be compressing the inlet feed to bed 1 along with your recycle stream instead of just your recycle stream. The amount that will need to be cooled also increases. So as I said, the configuration that we have set up is the most common and most energy efficient, but this configuration does require low amounts of CO2 and water. So that is the only stipulation. Each reactor, so bed 1, bed 2, bed 3, each one of these beds should achieve about a 20 to 25% conversion per pass. So we can look at that a little bit later, but each one of these should be targeting about 20% conversion. After we pass through all three of these beds, this condenser cooler will drop out that ammonia, and then we'll send it through to a couple of other condensers to give us a high purity ammonia stream. The last thing I want to note about the process is that we will have inerts in this system, mainly argon and methane are going to be the inerts for this system. So the introduction of a purge is going to be necessary. We don't want inert buildup, so that purge stream will help us remove some of those components. We generally see we want to maintain about a 15 mole percent inert in the system. All right, so now that we've covered the process, we can move on to the ProMax side of things. So the inlet to our bed 1 reactor is coming in at 273 degrees Fahrenheit. As I said earlier, this reaction typically operates at about 750 to 900 degrees. It is so low relative to the reaction because we just cooled it to drop out our produced ammonia. So we will have a preheater before bed 1 to bring us up back to operating temperatures. So that's one thing to note. Notice we are at very high pressure and our composition. So here we have about 24% nitrogen and 64% hydrogen. From our stoichiometric equation, we can see that we have about a 3-to-1 ratio, just like we want, which is great. And we do have a small amount of inerts here, 9.5%. So let's talk about, we've talked about the inlet. We can go ahead and move on to the temperature specifications. As mentioned, we want to target, we're going to want to target an outlet temperature of 910. This is saying that we have a temperature controller on the outlet of the reactor, and we're supplying as much cooling needed to produce that temperature. Again, because this is an exothermic reaction. So to simulate that, what we're going to do is we're going to add a calculator on the inlet temperature to solve for that 910 outlet. We could simply sit here and guess inlet temperatures until we reach 910, or we can add a calculator, which will save us some time. So to do that, we will go to the inlet stream to bed 1. And as you can see, our temperature is unspecified, and it's also a white square, meaning it is free to specify. Any of these gray rectangles won't allow us to specify anything. These are values that are calculated by ProMax. Okay, so back to that temperature. To add a calculator, we will right-click and create simple solver. We'll want to name the simple solver. Let's see, bed 1 outlet temperature. The next thing we'll want to do is we'll want to create a function that's going to relate the outlet temperature to what we're targeting. So to explain the solver a bit, I will open up a Word document. How ProMax works is based on an error function. The equation that we're trying to target is we want the, T outlet to equal 910 degrees Fahrenheit. How the solvers work is what we want to do is solve this equation to 0. So to solve for 0, we'll simply subtract 910. So this part is what we're going to want to put into ProMax. And what ProMax is going to do is it's going to iterate different inlet temperatures, changing the outlet until we have an error of 0. This calculator is just going to change the inlet temperature until our outlet temperature is within 0.001% of 910. And this is what we'll want to input into ProMax. So T outlet minus 910. And you can see here, this is where that residual error will be calculated. We will then want to tell ProMax what T outlet is. To do that, we'll go to our measured variables window and click add. The stream that we want to target is going to be stream 2, that is the outlet of bed 1. We'll go through our moniker tree to locate the temperature. And then label this variable the same as the variable in the function, capital T, outlet, no spaces. And add. So now we have defined the function, found that variable within ProMax. The last thing we'll want to do is specify a guess. This guess is going to be a starting iterative step. So this is going to be the inlet temperature of bed 1. And we're simply just applying a guess. We know that the temperature is generally between 750 to 900. So let's start with the lowest temperature of 750. And something to note is this callout box that we have on stream 5 has a pound sign on it. The pound sign indicates that we have a calculator placed on that stream in that variable specifically. We can now move on to the reaction side of things. As mentioned earlier, we're going to be using a kinetic reaction for this reactor. And I would say this is probably the most involved way to set up a reactor. There is a lot of inputs that are required, but it is a very, very valuable way to do it if you take the time. It will give us a lot of really good information and help us match what is truly going on within your reactor. The first thing we'll want to do when using a kinetic-based reaction is go to our project viewer. On the left side, navigate to reaction sets. I have already created a reaction set for us, but we can go ahead and walk through it. I like to think of this like a LinkedIn page. This is the profile that is going to tell us how hard this reactor is going to work, what it does, and how it behaves. So we're going to first work, the first thing we'll need to set up a kinetic-based equation is to input the components. Simple as that. This is like the profile picture. What is going on within that reactor? So we can simply type in the components. We have hydrogen, nitrogen, and ammonia. Once we've specified those components, we will need to input the stoichiometric coefficients. So we know that 3 hydrogens react with 1 nitrogen to produce 2 ammonia. The negatives here are going to dictate components that are being consumed. So we know that hydrogen and nitrogen are going to be consumed, therefore they're negative, and ammonia is being produced, therefore positive. We will then want to specify the forward and reverse reaction coefficients. Something that might be a little confusing is these are not from stoichiometry. These come from empirical data, so they look a little bit different. This information, along with the kinetics, is found in the optimal thermal design of autothermal ammonia synthesis reactor. Okay, so we have negative 1.5 for the 1 and negative 1 for the forward, and negative 1.5, 0, and 1 for the reverse. Now that we've specified that, we can move on to this sidebar. This is where we will input the kinetic information. So we know this is a forward and reverse reaction. The kinetics are going to be, the concentration type is going to be partial pressure with units of bar. The kinetic base that's used is nitrogen with rate units of kilomoles per meter cubed hour. And we will be using the Arrhenius equation for this. So we'll need to specify the forward kinetics as well as the reverse kinetics. Now this is only because it's a forward and reverse reaction. If you know this is an equilibrium reaction, you'll simply specify the equilibrium coefficients. If this is just a forward, you'll specify forward. There's multiple different ways to do this setup. We can also add adsorption terms over here to the left. So this is a very detailed approach to the reactor, and there's multiple ways to do it. But for this case, we just have a forward and reverse reaction. So again, these kinetic values come from that paper that I said earlier. We'll input those values here. And click OK. So now we have our reaction kinetics set up. We're good to go. And for just a quick review, we have the Arrhenius equation here in the bottom left-hand corner. Those units that we talked about are the units of K. And the pre-exponential factor, it was K naught instead of A. So just something to note. Okay, so we've set up that reaction. Now we can set that reaction within the reactor. Okay, so let's move on to bed 1. The first thing we'll need to do is specify a type of reactor. From the drop-down, as you can see, there's multiple different kinds of reactors that we can use. There's conversion, equilibrium, Gibbs minimization. Today, we'll just use a plug flow. And then we'll choose our reaction set. We only have one reaction set here, so we'll choose ammonia production. Could you please define plug flow? Something really handy in ProMax is if you right-click on something that you're unsure of, like for the type, you can click "What's this?" and it'll give us a brief description of what's going on here. As you can see, it just tells us what kind of reactors we have. We can also click the question mark in the top of a window, And it'll take us to the help. Here we can type in plug flow reactor. And it'll give us a description of anything that you're looking up. So plug flow reactors can be used to model tubular flow reactors in which there's no mixing in the horizontal direction. And then it tells you that we need some kinetic information. And then I'll walk you through setting up the reactor with an example, walking you through the kinetics that we just did. So the help is very helpful if you ever run into any questions like that. Okay, so we've set up the reactor with the kinetics that we previously set up. We can now move on to the hardware. Okay, so for this reactor, we are saying that it is 4 feet in length with a 22-foot diameter. It's a singular tube, 2-inch thickness, 1 pass, and the void fraction is going to be 40%. A void fraction is the space not taken up by the catalyst. So this is where no reaction is taking place. And again, if you forget what void fraction is, you can right-click, what's this? And it'll give you a brief description of what void fraction is. So we've fully specified bed 1. Now we can go ahead and execute. And as you can see, it's iterating through changing that inlet temperature to meet our 910 degrees Fahrenheit. So we did hit that as a target, and the required inlet is 740 degrees Fahrenheit. We started with 750, I believe. Another thing to note, we came in at 1.87% ammonia, and we now have 8%. So bed 1's doing exactly what it needs to do. We can also go into bed 1 and look at the percent conversion of nitrogen and hydrogen. So now we're going to go ahead and repeat the same steps into bed 2 and bed 3. We're going to do the same thing to the inlet temperature of bed 2, which I've already done for us. This blue box indicates a calculator. So we'll show calculator, and again, we're going to be targeting an outlet temperature of 910 degrees. We will just need to specify bed 2. Again, it's a plug flow reactor. The reaction set that we want to use is ammonia production. We'll just need to specify the hardware. Again, 4 feet in length, 22-foot diameter, 1 tube with a 2-inch thickness, and 40% void fraction. We can then execute bed 2. A perfect 910 degrees Fahrenheit on the outlet. Let's look at what that inlet temperature. Okay, so with an inlet temperature of 819. Okay, and then the same thing, we'll do this again for bed 3. So again, I set that calculator up to target 910 on the outlet. The hardware has been set up. We have plug flow and ammonia production as our reaction set. We can execute that final reactor. We now are cooling stream 8 to 857 to target 910. And we have produced 13.3% ammonia. So the last thing we'll want to do is we will want to, okay, so we've produced our ammonia. What's going to happen now is it's going to come down to this chiller, chilled in 9 to 90 degrees Fahrenheit. Go to the compressor to drop out our ammonia. You can see we're at 98.91% ammonia. Let's go ahead and execute these blocks. So our final product is 99.9% mole fraction ammonia. But we still haven't implemented this recycle with the purge. As I said earlier, we want to make sure that we include the purge to make sure we're never above 15%, 50 mole percent inerts. So I have simply set a 1.5% purge on stream 14. So stream 14 is going to come to the separator where 1.5% will get split off and purged. And then get sent to a compressor. This compressor is what's going to help us get back up to the pressure, our inlet pressure, because we're currently at, let's see, 2100. I'm not sure what is typically used for the cooling duty. Okay, so we want to get back up to 2200. So a very easy way to set this up is using a simple specifier. It's similar to a solver, but what it's going to do is it's going to take the pressure that we're targeting, so the pressure in stream 3, and set it in stream 17. We could do that manually by simply 2240 by simply putting that into stream 17. But what happens if something changes upstream and that pressure varies? ProMax wouldn't be able to set that correlation up. If we set a simple specifier, that correlation will always be set, and that compressor will change based on the inlet pressure. So to do that, we will again right-click, create simple specifier. And this is different than a solver, so the only thing we'll need to do here is input the correlated function. So all we'll need to do is type in the variable that we want to correlate it to. So P inlet. We will need to tell ProMax what P inlet is in our independent variable. Let's see, the stream that we are concerned with is stream 3. We want the pressure, and we will call this P inlet. And you can see here that it has called that variable. So 2240, it's exactly what we were targeting. And we are now free to execute the project. So that is the complete walkthrough of the kinetic-based reaction, as well as a couple of solvers and specifiers. Well, thank y'all so much for joining. It was a pleasure walking through this with y'all today. And y'all have a good day.